Good morning and welcome to the Royal Swedish Academy of Sciences and this press conference about the Nobel Prize in Physics. It's good to see all of you here today, and I would also like to welcome all those who are watching this press conference over the internet or on TV. I'm Göran Hansson. I'm the Secretary General of the Academy, and with me today I have two members of the Nobel Committee for Physics. On my right, Hansson, who is the chairman of the committee, and on my left, Professor John Wettlaufer, who is also a member of the committee. The Academy met in session this morning. We have taken the decision on the Nobel Prize in Physics. We have contacted the laureates, and now we're here to tell you about it. I will read the announcement first in Swedish and then in other languages. Professor Hansson will make some remarks on behalf of the Nobel Committee, and Professor Wettlaufer will present to you the science behind the prize. Kungliga Vetenskapsakademin har idag beslutat att utdela 2021 års Nobelpris i fysik för banbrytande bidrag till vår förståelse av komplexa fysikaliska system. Den ena hälften av priset utdelas gemensamt till Shukuro Manabe och Klaus Hasselmann för fysikalisk modellering av jordens klimat, kvantitativ analys av variationer och tillförlitlig förutsägelse av global uppvärmning. Den andra hälften av priset går till Giorgio Parisi för upptäckten av hur oordning och fluktuationer samverkar i fysikaliska system från atomära till planetära skalor. The Royal Swedish Academy of Sciences has today decided to award the 2021 Nobel Prize in Physics for groundbreaking contributions to our understanding of complex physical systems. One half of the prize is awarded jointly to Shukuro Manabe and Klaus Hasselmann for the physical modeling of Earth's climate, quantifying variability and reliably predicting global warming. The other half goes to Giorgio Parisi for the discovery of the interplay of disorder and fluctuations in physical systems from atomic to planetary scales. Die Königliche Schwedische Akademie der Wissenschaften hat heute beschlossen, den Nobelpreis für Physik des Jahres 2021 zu verleihen. Eine Hälfte geht gemeinsam an Shukuro Manabe und Klaus Hasselmann für das physikalische Modellieren des Klimas der Erde, die quantitative Analyse von Variationen und die zuverlässige Vorhersage der Erderwärmung. Die andere Hälfte geht an Giorgio Parisi für die Entdeckung, wie das Zusammenspiel von Unordnung und Fluktuationen physikalische Systeme von der atomaren bis hin zur planetarischen Ebene bestimmt. L'Académie royale des sciences de Suède a décidé ce jour d'attribuer le prix Nobel de physique 2021 avec une moitié conjointement à Shukuro Manabe et Klaus Hasselmann pour la modélisation physique du climat de la Terre, l'analyse quantitative des variations et la prédiction fiable du réchauffement climatique. Et l'autre moitié à Giorgio Parisi pour la découverte de comment le désordre et les fluctuations interagissent dans les systèmes physiques d'échelle atomique à planétaire. Korolievskaja Akademija nauk решила сегодня присудить Нобелевскую премию по физике одну половину Porvnu Shukuro Manabe и Klaus Hasselmann за физическое моделирование климата Земли, количественный анализ вариаций и надежный прогноз глобального потепления. А вторую половину Giorgio Parisi за открытие того, как беспорядок и флуктуации взаимодействуют в физических системах от атомных до планетарных масштабов. And you see the new Nobel laureates on the screen above us. Here are some brief biodata. Shukuro Manabe was born in 1931 in Shingu in Japan. He got his PhD from the University of Tokyo, and he is, since many years, senior meteorologist at Princeton University in the United States. Klaus Hasselmann was born in Hamburg in Germany, also in 1931. He got his PhD from the Georg August Universität in Göttingen, and he's now at the Max Planck Institute for Meteorology in Hamburg. Giorgio Parisi was born in 1948 in Rome, in Italy. He got his PhD at La Sapienza Università di Roma in 1970, and he remains at La Sapienza as professor. With that, I'd like to ask Thors Hansson to make some remarks on behalf of the Nobel Committee. Hans, please.
Thank you. So, many of you might believe that physics is only about simple and ordered phenomena, like the Earth in its perfectly elliptical orbit around the sun, or atoms that are in perfect crystal structures, or electric currents that flow predictably from the socket through the lamps or to your refrigerator. But physics is much more than this. One of the basic tasks of physics is to use basic theories of matter to explain complex phenomena and processes. Like how materials like glass are structured, or what is the development of the Earth's climate. These studies require deep intuition for what structures and what progressions are essential, and also mathematical ingenuity in order to develop the models and the theory that describes them. Things at which this year's laureates are true masters.
Thank you, Hans. John Wettlaufer, please tell us more about the science behind the prize. The floor is yours.
Thank you. From a distance, complex physical objects can appear simple. From atoms to planets, taking a closer look always reveals structure. We are awash in complexity at every scale that we observe. As scientists, we ask, how much detail is required to explain the observations? Must we track every water molecule to explain the ocean? What length scales are important to understand if we are going to see what phenomenon emerge from such a system? One half of this year's prize focuses on the physics of Earth's climate. That's an old topic in physical sciences. It began in 1824 with Fourier. Fourier recognized that the atmosphere of Earth is ostensibly transparent to the visible radiation from the sun. And yet the Earth converts that visible radiation into what he called dark heat, the dark energy of Fourier's time. He surmised that this must interact somehow with the atmosphere to keep Earth warm. Scientists subsequently measured in the laboratory the absorption and emission of what we now call infrared radiation, Fourier's dark heat. And it was to take 70 years before Svante Arrhenius took these observations and these measurements and combined them in the first mathematical model of climate. And he predicted that if the concentration of greenhouse gases in the atmosphere increased, so too would the temperature of the Earth. Another 70 years, 2 world wars, and the computer revolution would pass before Shukuro Manabe and his colleagues knit together this web of processes, including key aspects of the atmosphere's thermodynamics and dynamics, and made the first prediction, reliable prediction, that if you double the carbon dioxide in Earth's atmosphere, the Earth's surface temperature would increase by 2 degrees Celsius. And about the same time, Edward Lorenz taught us about chaos, that the weather is chaotic. It evolves rapidly and becomes unpredictable after about a week. Could it be that Lorenz's chaos was noise to the climate? So thought Klaus Hasselmann. He made the analogy between the rapidly varying weather and the slowly varying climate and Brownian motion from Einstein's theory, whereby rapid collisions of water molecules with pollen grains displace them slowly over time. He then predicted that the weather on timescales of days influences the ocean on the timescale of years. He went further with these ideas, and he constructed a systematic statistical way to compare measurements, observations, and models to extract the fingerprints of particular physical processes in the climate system. Galileo peered into outer space with his telescope. Giorgio Parisi peered into inner space with mathematics and asked questions about apparently banal materials like glass that were deep and impacted many areas of physics. We're used to taking a liquid like water and cooling it under normal circumstances. It freezes into a periodic, well-ordered structure. However, if we freeze the liquid very rapidly, it becomes another body. We call it amorphous. It has attributes of both solid and liquid. We can understand the difference between these systems in daily life because we see them in glasses all the time. Glasses fracture like a solid and yet flow like a liquid. We can consider their energies, their energy landscapes. The periodic solid has a simple landscape. A particle in a bowl can only find one place to rest. In a glass, the landscape is complex and rugged. It's not clear where particles will reside. They are frustrated. Giorgio Parisi studied a magnetic version of a glass called a spin glass. Imagine that we can decorate this triangle with magnets that can either have their north poles up, north poles down, or they can flip between north up and north down. Okay. However, we have the stricture that no two corners can have the same orientation. So when we place the third, it breaks the stricture, it breaks the rule. So another one must flip, which drives the flipping of another one, and so forth, forever. The system is perpetually frustrated. Giorgio Parisi tamed this frustration, this complicated landscape, by building a deep physical and mathematical model which was so broad that it has impacted a vast range of fields far beyond spin glasses. From how granular materials pack, to neuroscience, to how we compute, to random lasers, and to emergent phenomenon far beyond what he envisioned in the 70s when he started this work.
Thank you very much, John. And it's now time for questions from you, ladies and gentlemen, in the audience. We hope to have one of our Nobel laureates with us, but I don't know if he is on yet. He is. Okay, very good. Professor Parisi, are you there?
Yes, I'm here.
Very good. Thank you for being with us. We are in the midst of the press conference.
Welcome. Thank you to you.
Okay, you have watched it. Very good. And now we have journalists from Sweden and all over the world, and I'm sure they would like to ask you some questions. Who would like to start? Thomas von Heine,
Thank you.
Swedish Radio, Swedish TV.
Swedish Television Public Service. Congratulations, Professor.
Thank you.
I'm curious, your part of the prize seems a little bit different from the others, but there is a connection, I'm sure. Could you describe the connection between your half and the other half?
Well, during my work, I have studied many effects of disorder fluctuations. And for example, in about 40 years ago, I did introduce a new phenomenon, what is called stochastic resonance, together with Benzi, Sutera, and Vulpiani. That was supposed to give a qualitative description of the phenomena of glaciation, of big glaciation, and give some qualitative explanation of the periodicity of qualitative and quantitative explanation of the periodicity of 100,000 years. So this idea, this was not directly related to spin glasses, but was part of my study of interplay between fluctuation in physical system.
Thank you.
Thank you. David Keaton over there.
From the Associated Press. Congratulations, Professor, on this award. This award comes just a few weeks before the COP26 kicks off in the United Kingdom. Do you have a message for world leaders that will be gathering to take decisions on ways to limit climate change, given the work that you've done, and today as a Nobel laureate, do you have a message for them?
Well, I think that it is urgent, it's very urgent that we take a very strong decision and we move a very strong pace, because we are in a situation where we can have negative, positive feedback, and that may accelerate the increase of temperature. So it's clear that for the future generation, we have to act now in a very fast way, and not with a strong delay.
Thank you. We have to act now. That was the message from Professor Parisi. More questions?
Yes, sir.
Yes, gentleman over there.
Yes, Daniel Ingmo, Express, and congratulations, Mr. Parisi. I would like to ask you,
thank you,
if you were expecting this award and how you reacted when you got the news.
Well, I was very happy. I mean, in some sense, I was not really expecting, but I knew that I have some chance, and so I kept the telephone near me. But I was expecting that phone call, was not expecting the phone call so early, but I was really very happy. I mean, I was not expecting, but I knew that there was some non-negligible possibility.
Right. Any more questions? Yes, Maria Gunther.
Yes, this is Maria Gunther from Dagens Nyheter. Congratulations to your prize. You have been working in many different fields in physics. What are you working on now?
Well, I'm working on, for the present moment, I work to understand better the physics of glasses. There are many questions that are not really understood. And also I'm doing some part of the time I'm following the pandemics of COVID, try to understand more precisely which is the situation, which is the correlation between different events and so on, because you see once that one has events, this data, big data, it is very important to follow with different techniques, with different viewpoints.
Yes, are there more questions? David Keaton has one more question, and then don't be shy, the rest of you. You have your chance now. David Keaton.
Thank you. David Keaton again from Associated Press. 2021 saw a great number of extreme weather events, from storms, floodings to heat waves. In your opinion, Professor, how important is it to truly understand weather patterns, and how can this understanding help prevent further catastrophes?
Look, there are many, many things that we do understand by weather, and also with the fact of the contribution of the other two, or Sukuru, or Manabe, Klaus Assmann. So this is very important. It's clear that there are still some details that we have to understand, because we have to understand the role of ocean and so on. But what is quite clear that the effect of climate changing is that more energy is emitted in the atmosphere, and if you have more energy in the atmosphere, the chance of extreme event is going to increase very strongly.
Thank you. Are there any more questions to Professor Parisi? Yes, one more question, please, lady over there.
Anneli Megner-Arn, TV4, congratulations on the prize. Yes, I wonder, when you find these spin glasses and how they fluctuate, is it a little bit like artificial intelligence? I mean, there are so many different ways in which they can form, so I wonder if you can shed some light on that, how you sort of get into the clue of this.
Well, the point is that glasses, a system like glasses, are very familiar in nature, and also complex objects that we normally see, but we don't recognize as complex. So one has to make from one side some kind of general theory, and some specialize this theory to the particular object that you want to study.
Great. There we got some light through the spin glass. One more question. Yes, from Lundagård, students' newspaper in Lund University. Please.
Yes, thank you so much, and congratulations on the prize. As a student magazine, we're wondering, how will you celebrate this prize?
How do I celebrate? Well, I really had not the time to think about, because also with COVID restriction, we cannot have a very big celebration, but I think that I should do something, but I'm not really decided.
Well, Professor Parisi, when you can travel again, I'm sure the students in Lund will throw a great party for you.
Yes, we will.
Oh, yes, I believe so.
Thank you. We're glad to have you.
Any more questions to Professor Parisi? If not, thank you very much, Professor Parisi, for being with us at the press conference, and congratulations again to your Nobel Prize.
Okay, thank you so much. Goodbye.
Bye-bye. And now, are there any questions to the panel? Please, Holly.
Do you want me to ask in Swedish or English?
We can continue in English.
Okay. As been said, these are quite different prices. What is the link between them?
Hans?
So it is a divided price. We should say that first. It is two pieces to this price. But there is also, as you saw, it was an overreaching, description of the price, which indicates that although these are two parts, two different prices, it's divided into two, it's not one price. But there is the common theme that has to do with disorder, that has to do with fluctuations, that has to do with how disorder and fluctuations together, if you understand it properly, can give rise to something that we can understand and something that we can predict. We can predict what is happening with the climate in the future if we know how to encode the chaotic weather, as Professor Wettlaufer told you about. And in the spin glasses, although it's a very complicated system, it's a hidden structure that you can discover if you analyze it in the correct way. And the correct way to analyze it was exactly what Professor Parisi discovered.
Any more questions? Yes, Lunda går again.
Thank you. So with this prize, are the committee hoping to send a message to world leaders about the gravity of the climate crisis?
Well, the world leader that hasn't gotten the message yet, I'm not sure that they will get it because we are saying it. But it's a physics prize. And what we are saying is that the modeling of climate is solidly based in physical theory and well-known physics.
Yeah, you could say that the notion of global warming is resting on solid science. That's a message. John,
Thank
you want to add?
I'll just emphasize that we have recognized here, I think, as you may have seen in the presentation, the real core of how climate has been understood and modeled from sort of its inception. And so our message is that we believe in physics, and that we're recognizing that emergent phenomena sometimes require you to look at all the individual complicated physical mechanisms and knit them together to make a prediction. And back to the question here, the overarching theme really does wed these two approaches. Giorgio Parisi's work looks at the underlying disorder and fluctuations and predicts emergent behavior. And the link between his work and Shukuro Manabe's work is the recognition by Klaus Hasselmann that fluctuations are key for predictability. And so we do not understand predictability unless we understand variability. And that's a key here.
Thank you so much.
Thank you. More questions? If there are no more questions to the panel, we close this part of the press conference, and now there will be opportunities for interviews with experts for those of you who have requested such. Thank you very much for your interest, and perhaps we'll meet again tomorrow. Thanks.